Hello everybody, this should be the last video for chapter 17 homework number 1 unless we proceed the time limit on this video. Alright, but exercise 17.31. For each reaction, calculate the delta H, delta S, and delta G at 28 degrees. Just so you guys know, this 28 degrees has to be converted to Kelvin, so plus 273. And that doesn't come into play until the final stage with delta G. Anywho, so we all know how to solve for the delta H. Remember, it's products minus reactants, right? So let's do that. We have bracket 2 times NO2 gas minus N2O gas. Alright, so now we plug in the values. For me, I have delta H equals 33.2, and I have delta H equals 9.16. Sorry, this is for NO2. And this is for N2O4. Alright, so here we go. Well, if we plug in these values, we know how to do this. 2 multiplied by 33.2 minus 9.16. So we get 66.4 minus 9.16. We'll get something around 57.24 kilojoules, right? So that is the delta H value. So right now, just keep this on the side of your paper. Well, more or less this one right here, because we'll be having to use this formula to find the delta H coming up later in this problem. Part B of the problem wants us to find the delta S, and you can solve that the same way you solve for the delta H. It's products minus reactants. So products minus reactants. So we know what this is already. It's 2NO2 minus N2O4. So what are the values and everything? For the delta S is 240.1 for NO2. Delta S for 304.4 for N2O. Now, these values right here aren't calculated. They're in the back of the book. Like A7, I think they maybe start, so I don't want to write that down because I'm positive. But anyways, let's solve this problem, though. We have 2 multiplied by 240, because remember, products comes first for this part, 240.1, minus 304.4. Now, when I calculated that out, I got a value of 175.8 joules per Kelvin. Now, it's very important to remember that this is in joules. So when it comes to Gibbs free energy, we're going to have to convert that, right? Alright, so let's go do the next problem, or next part C of this problem. This next part wants us to solve for the delta G. We know from previous slides for other videos, we have delta G equals delta H minus T times delta S. So just by looking at this formula, we know that temperature has effect. Let me just rewrite that. So we know that delta T right here, T has effect on the delta H. And we remember that delta G equals positive equals not spontaneous. Delta G equals negative equals spontaneous. So let's just plug the values in. We have delta G equals, now if we look back, we calculated that the delta H value equaled 57.24. And the delta S value equaled 175.8 joules per Kelvin. And I believe the temperature they told us to test for was 28 degrees Celsius. So there's a few conversions we have to do. Delta H has no conversions, that just gets plugged in. 57, one second, so let me just write that here. So we have more room. We have the delta G equals the delta H, which was calculated to be 57.24 minus the temperature has to be converted to Kelvin, so 28 plus 273, I got around 301, multiplied by the entropy, which is in joules, which needs to be converted to kilojoules, which is 175.8 times 10 to the minus 3. Alright, so when you go through these calculations, I got something around 4.3 kilojoules. The next question asks, can this reaction be made spontaneous if you play around with the temperature, like if you increase it or decrease it? Well, remember that this reaction right here is non-spontaneous, right, because it's a positive value. Because positive correlates with this guy over here. It's not spontaneous. But if we play with this function right here, we know that if we increase the temperature right here, so say we have a temperature of like 350, what would happen? The entropy would become a high negative value, and then that value multiplied by 350 subtracted from the enthalpy would become a negative value. So just try it out if you really want to. It's hard to explain this, so just try it out with delta G equals 57.24 minus, say, a temperature of 350 multiplied by 175.8 times 10 to the minus 3. Calculate that out, and if you do that out, you'll notice that the delta G becomes negative. And since it becomes negative, it means this reaction can be made spontaneous if you increase the temperature. Alright guys, this last one, exercise 17.37, is an example of Hess's law. So Hess's law doesn't just work for enthalpy, it also works for Gibbs free energy. So this is Hess's law. Alright, so let's just look at this. We have the products right here, the reactants right here, products right here. Let's look at the first reaction. We notice that right here we have this value is in the products, but over here it's in the reactants. So what do? We flip that one. So let's go ahead and do that. We have Fe2O3 solid would equal 2Fe plus 3 over 2 O2 gas. And now the delta G value will also flip to 742 kilojoules. In this next one, if we look at this, we notice that it's in the right order. CO2 is in the products, like it is over here. However, this has a 3 CO2. So what do? We multiply this by 3. So this comes out to be something like this. We have 3 CO gas plus 3 over 2 O2 plus 3 CO2 gas equals 3 times negative 257.2. Alright, so let's see what cancels out and goes. We notice that this, so let me just erase that real quick. We have 3 O2 gas. Let's notice that this cancels out with this. Alright, so now let's bring down what we have. We have Fe2O3 sorry, plus 3 CO solid, so that's taken care of, equals 2 Fe comes down, and then 3 CO2 comes down. Now you notice that this is equal to what it is up here. So now we solve for it, it would just be 742 plus 3 times negative 257.2. And when I calculated that out, I got negative 29.4 kilojoules. Alright. If you have any more questions, email me or talk to me in class. Thank you.